Good afternoon, everyone. I can see that people are starting to enter our little room here, and welcome to IT Masters webinar on AI and hopefully how to know when AI lies. I'm going to just let everybody sort of fill into the room for a little while before we actually start. But those of you who may have done some of our courses before might remember Luca, who is our presenter today, our mentor.
Hello.
Luca's coming to us all the way from Canada today, which is fantastic, and it's very lucky that he's in a time zone where it's a reasonable thing to happen. We will get started pretty soon. Just remember a few things, bit of housekeeping. In the chat on the webinar, please set your chat to everyone and say hello. Tell us where you are, what you're doing. I know it's lunchtime for most people here in Australia, but maybe you're from overseas as well. But yeah, we'd love to see what you're up to at the moment, and maybe give us a little bit of a note if they've got any particular things that you're interested in understanding as part of this. And as always, we don't use the raise hand, so just don't bother with that because we will ignore it. But please use the Q&A when you've got questions that you would like Luca to answer. If you've got questions about the webinar itself, when it's going to be up on screen, all of that sort of stuff, just put them in the chat. We'll put messages in there. But essentially, this is being recorded, and all of the details will be sent out in the next 24 hours, including a link to the recording, which will be on our YouTube channel and on our website. So you'll be able to actually have a look at and listen to it later on if there's more information, or you want to share it with your friends. We're very keen. And yes, it is very windy here in Victoria, in Melbourne at the moment. I've heard all sorts of stories about trees being down for those of you interstate or overseas. But I can see that most people here today are actually from Australia, because it's a very bad time for most other people overseas. I think we get a lot of people from Africa and India, and they would be either having breakfast or still asleep at this time. But anyway, I think a few people are here now. So with all of that babble out of the way, I'd like to introduce you to Luca Ewington-Pitsas and to say good day. How are you, Luca?
Very well, Shane. Very glad to be here as always. It's always very fun doing these courses. Just a little introduction on myself. I'm a two-time startup founder, currently working as a senior data scientist at Sharvik AI in Melbourne, and I'm currently in Canada. At the moment, I'm doing some independent research on sparse autoencoders, which are sort of a way to scan into large language models and work out all the intricate stuff that's going on in there. And that's kind of going to be the focus of this talk today. That's going to be the idea.
Excellent.
Are we still just waiting for people to filter in, or
no, I
or
think
should we?
let's kick it off and get going.
Okay, excellent. Well, if anyone has any great questions, just chuck them in the chat. But otherwise, we'll get going. Okay, so welcome everyone. Thank you so much for making it. Thank you for taking lunchtime to check this out. So what we're going to do today is we're going to talk about how we're finally getting to a point where we can tell when a large language model is being dishonest to us. This is something that we haven't really been able to do until now. And the overview of the steps we're going to take is, firstly, we're going to talk about how language models work. Then we're going to talk about the problem of deception and hallucination. Then we're going to talk about polysemanticity, which is a long word, but it's like a fun word that you can try to remember in future. It's like a cool word you can impress people with. But essentially, this is one of the reasons it's very hard to work out what's going on inside the models. And we're going to have some really cool visual demonstrations. We're going to have some links. I assume everyone has access to these slides at this point. And if you do, please feel free to go and click the links yourself. Then we're going to talk about sparse autoencoders, which is a way around this problem. And it's a way to make what's going on inside these models monosemantic. So to sort of pick out single units that have interpretable meaning. And then finally, we're going to look at some research that was published in May of this year, so steaming hot off the presses, by Anthropic, who are one of the very, very big companies, just a little smaller than OpenAI, in the LLM space. So that's the overview of what we're going to do. And I'll just plug on. So, and I think I might kill the chat just for now, because it's taking up the screen. Okay, so how do language models work? There's two views that you have to keep in mind. And I know a lot of us probably know this already, but I'll just briefly cover it. So there's the outside view, which is the model, any kind of AI model, any kind of machine learning model is a big complex machine that is someone's made it, and who knows how they've made it, and it's terrifyingly complicated. But all we need to worry about is that we can give it inputs and that it gives us outputs. And this is, in my opinion, like a very, very good way to think about artificial intelligences, because it cuts away a lot of the complexities. So in the case of language models, the input is a sentence, like this one, and the output is a sentence. And somehow the box in the middle, which we sometimes refer to as a black box because we can't see into it, gives us an output that actually seems good and reasonable. Okay, so that's the outside view. And then there's the inside view. And this is that inside that black box, there are many, many different kinds of neural network architecture that could exist. But in general, you want to think about it as kind of a web like this, kind of a graph, where you somehow turn your input into some numbers and you feed those numbers into the first layer of the graph. And then that information gets fed through this very, very complex series of layers and then comes out with the output that you wanted. Shane, do you think maybe in like 5 or 10 minutes, we should have like a questions time? Would that be a good idea, you think?
If we've got questions, by all means. I can think of a whole pile at the moment, but yes.
Okay, cool. So if you have questions, post them in the chat, and then in 5 or 10 minutes,
post them in the Q&A though, because then we can differentiate them out from the chat. Makes it a bit easier.
Right. Okay, excellent. Okay, so this is kind of what the neural networks look inside. And here we're coming to our first kind of visual demonstration. So this is animation that was made by 3 Blue 1 Brown. Does anyone know who 3 Blue 1 Brown is? Because I do, and he's sick. He's like one of the coolest people online, in my opinion. Anyhow, so this is a demonstration of a much older, much smaller neural network, one for classifying images. And all that happens is you break the image up into pixels. So let's say the image has 768 pixels in it. You take every pixel, you feed it into the first, or 784, you feed to the first layer. The first layer feeds the second layer, so on, until you finally get to the last layer. And the last layer has 10 neurons exactly. And whichever one lights up, that's the classification that our model has decided to give us. So this is kind of what's happening inside. Again, if you go to this link, you'll see the full explanation, and it's really good and really helpful. But this is what is going on. Something like this is what's going on inside of the language model that we saw before. The only difference is that language models are what we call autoregressive. So that's like a key term for this lecture, I guess, is that they predict one token at a time. So from your perspective, you give something like GPT, which is a famous language model, you give it a sentence and it gives you back a sentence. But what actually is happening underneath the hood is your sentence gets broken up into numbers, which are passed through the network, and then a single word comes out the other end. And then that word, which is the next word in the sentence, gets pasted onto the end of your sentence that you put in, and then it gets passed through again. And then we get the next word, and so on and so on and so on. And this is what makes this model autoregressive, is because it does one at a time, predicts the next thing, the next token one at a time. So that's hopefully gives us a little bit of an idea of what's going on inside these models. We can kind of think of them as a black box, but inside they're this sort of complicated network of neurons, and they perform in an autoregressive fashion, they give you your output sentence. And this, of course, is why when you use GPT or Claude, you see the output. It doesn't appear all at once. It appears one token at a time or one word at a time. It sort of types out. Okay, so this is how language models work. Now let's talk about deception and hallucination. So there's a lot of case studies where models have been shown not to give us the output that we want. In a lot of cases, it seems to give us good outputs, language models, but in a lot of cases, they don't. In particular, every time someone releases a new language model, there'll be people on Twitter who will jailbreak the model and make it tell you how to, create arsenic or a bomb, and don't look any of this up, by the way. but it'll tell you how to do things that you shouldn't be able to do, and they do that by injecting a specific prompt, and then the output comes. The bad output occurs because of that prompt. Now, an interesting thing about deception and hallucination and other issues with language models is no one knows why it's happening. And of course, this is considered very concerning, because if, as is the sort of the promise of AI, if we can allow AI to take on a lot of the responsibilities that we humans have at the moment, if we can allow that to happen, then we need to be able to know what's going on. We need to be able to triage incidents, and we need to be able to guarantee that the AI is not going to give us bad outputs when it really needs to give us good outputs. So, just a few examples would be having artificial intelligences monitor people's medical state and administer drugs, or having them, administer critical care to people who are in combat situations, or again, possibly, seek and destroy and actually issue commands to robots that have the capability to kill people. So in all those cases, we definitely need to know why things are going wrong, and we need to have ways of preventing things from going wrong. And so that's sort of the big problem that we're looking at today, is how do we prevent deception and hallucination? So until a year ago, there was basically no way. No one had come up with a good way. And still, the ways that we have aren't excellent. But there is one, which is we're going to get to, which is sort of showing some promise. So I'm going to go through these next 3 slides, and then we're going to have a little question break. But you might think, and this is something that my dad actually asked me a few weeks ago. We built the model, right? In all cases, we built GPT. Why is it so hard to work out what's going on inside it? You'd think that if you created the thing, that you could kind of tell what's going on. So I'm going to give you some demonstrations as to why maybe that's not the case. So firstly, we're going to take this interactive tool that was built by Adam Harley, and I really encourage you to go check it out, because it's very cool as well as being quite educational. This again is one of those digit recognizing models. And this is actually the model as it's laid out. All of these are the weights inside the model, and they form a big graph. And you can see the lines represent the connections between all the different nodes. So if we draw, let's say, a 0, all the light squares represent high activating nodes, where there's a lot of interest and a very high score at that node. And the black represents low scores. So if we just look at this 9, let's have a look at this 0 here. So in this case, the lines, some of them are blue. Hopefully you can see this. Some of them are blue. In fact, let's just zoom in more. So we can see some of these lines are blue, and some of them are lighter colors, and some of them are kind of darker colors. A lighter colored line means that this line is contributing a lot to the value of this final output. So we can kind of see that this weight here contributes a lot to the 0 that's coming at the end here. And this weight here, because it's kind of a blue, the string in between is blue, doesn't contribute as much. And ultimately, we're kind of getting like we're not getting a 9 we're not getting a 0 exactly in this one. We're sort of getting like a 9 or an 8 or a 0. It's sort of hard to tell which one is actually being selected. But this might, let me ask you a question, right? Let's say that it was your job now. You're an artificial intelligence expert. You're monitoring this model. A customer just gave you this input, this 0, and this was the output. Could you explain? You have all the information in front of you. It's all here. Could you explain why exactly it came up as a 0? How would you go about even starting to try to explain that? Like, why didn't it come up as 0? Or maybe we can even have one that's correct. Let's draw a 1. As you can see, different nodes are lighting up here in all these spaces. Could you explain why this was a 1? The answer is like, no. The answer is like, not at all. Absolutely not. Who knows? This is madness. There's just this huge sea of connections, and they all eventually lead to this outcome, but Christ knows what's actually going on. And this is a very simple neural network. In particular, what we can say is that what we're dealing with here is polysemanticity. And this is a word that comes from poly, which is like many, and semantics, which is meanings. And what it means is that each neuron here doesn't have a single concrete meaning. Like, ideally, what we'd want is for a single dot to light up whenever we draw a 1. And then we go, okay, that dot, that's monosemantic, which is the opposite of polysemantic, because it is closely tied to this one concept. Whereas what we're dealing with here is many, many different neurons are lighting up for the same concept, and the same neurons will light up for different concepts as well. So there's not just this single neuron that lights up for a 1 and then doesn't otherwise. And if we look, and we draw, we see there are lots of neurons lit up for the 1. If we draw a 0, oh God. If we draw a 0, some of the same ones are still lit up. So we're dealing with a very sort of polysemantic situation. The semantics of the outcome are broken up and split up across many, many, many different neurons. And each neuron participates in many, many different semantic outcomes.
Can I ask you some questions about this before we go on?
Please.
So many questions. So awesome. The first one is that your last 0, its guess is a 9 or an 8.
Yes, indeed.
So yeah, because it's interesting because it looks like it's trying to match it to models, but then the models are getting further and further away from what the actual drawing is.
Yes. Yeah, that's correct. So I mean, I would not be able to tell you at all why it came to that conclusion. And this is a very simple model. I don't know how many parameters it has in it. Probably something like, 2,000, 3,000, 4,000, might even be like 10,000 parameters. Large language models have like billions of parameters.
Yeah.
So if it's not clear what's going on here, good luck, basically.
It is interesting because if it's trying to mirror our thought processes, if you go back to draw your 1 again.
Yeah, let's do that. Boom, boom.
Now, what fascinates me is this time it's come up with a second guess of 7, which I totally understand that because that's what we would think. If it wasn't a 1, it looks like a 7. I did notice, though, in the first time around, the second guess was a 9 again, and for reasons that, I don't necessarily understand. So it is amazing that we even get close to like if you compare it to OCD is more accurate than this in some respects.
OCD, optical character.
Yeah. I don't know what
OCR.
OCR, sorry. OCR.
Yeah.
OCD's a depression.
So in this one, you can kind of see a little bit more what's going on, maybe. So you can see that in this case, all these ones are lighting up. So it's like, oh, okay, the network is aware that there's some sort of edge here. And it seems to be aware that there's an edge here as well. And so in these lower layer features, you can kind of see it. oh, it's kind of understanding little bits of something. But as soon as it gets up here, we lose all ability to explain what's going on. So this is a highly polysemantic situation.
Yeah. So interesting things from the chats. One was the 0 came up as an 8 or a 9 because the 0 was at the top of the little box, not centered, was
That's
their
probably the
belief.
case. Let's
And
test that hypothesis.
yes, and there's another hypothesis to test as well. Ah, even more different.
Let's try that again. We're not able to get it.
Oh no, that came up with an 8.
Oh,
So
there we go.
there you go. Same sort of thing. I also wonder if it's the way you draw it, if the machine takes note of the order in which you draw them.
In this case, it doesn't. In this case, the input is simply exactly, it's just this.
Yep.
It's just the pixels.
And somebody else is just asking if you put in a European 7, with the
What the
stick
hell's,
across the.
oh, yeah. Let's see. My dad draws 7s like this. So already it's confident it's a 7, but I guess this should make it more confident. I don't know.
I reckon it'll come up as a 4. There you go. 7 or a 4. Interesting. Anyway, that's probably not. That's probably only part way along the important stuff.
Yes. Oh yeah. So any more questions, or should we move on?
There's no more formal questions. There's a bit of chat about stuff. Somebody's drawn a 3, and the guesses were 5 and 2.
Yeah. So this is not a perfect model, by the way. This is like a small model for demonstration purposes. The actual models that do this in production are much larger and they're much more accurate. Okay.
It certainly makes me understand exactly why there's all the hoo-ha over the inordinate power drain and resources drain of AI.
Right. Yes. Because even this small one is pretty chonky. And I guess the point we were trying to hammer home was that it's very hard to work out what's going on inside these models. We've just seen one visualization of a very small model. Here's another great visualization of an equally small model. Again, it's this, it's another model for detecting hand-drawn characters. And this is one way you could visualize it. So each of these little dots represents a neuron, just like we had those neurons before. These dots here represent the input over here. And all the white strings represent connections. So if anyone is brave enough to try to tell me what is going on right now and why, why we're getting a 9, please speak up, because I'm lost. I am very lost.
Okay, I've got a formal question and also one of my informal ones. The formal ones, from an electronic component view, what actually is a neuron? Because neurons are what are brain cells, aren't they?
From an electronic components view, well, I'm not a master of electronics. I do know that in terms of computer science, a neuron is simply a number. So it might be a 0. It might be, in fact, let's get Excalibur on. Let's get Excalibur up. So this is how a neuron works. A neuron, let's say it might be like, this one might be 0.1. And let's say there's another neuron which is connected to it, and it's got 0.3 in it. And they're connected. And we have an input, and the input, is it's 1, just to make things easier, 1.0. Okay, so this is our setup. These neurons are part of the network. This neuron is an input neuron. So if we go back to that, Adam Harley's demonstration, so all of these are neurons here, and this is the input down the bottom. That's the input in this case. And what we're doing is we're imagining that this here is just one single dot of the input, like maybe it's the dot right at the corner here, or maybe it's this dot here in the middle. And it's connecting to one of these neurons as part of the computation process. And so like, let's say that this neuron, that might be like one of these neurons here. And then, because it's connected, you see it's connected. And then this neuron here, it might be like one in the next layer. It's connected here. Okay, so what we actually do is we say, okay, neuron, we pass it in, and usually we just multiply the thing that's coming in by the neuron. So we multiply it. 0.1 times 1 is 0.1. Okay, great. So that's the activation. That's what we call the activation. It's just come out of the neuron. And then we pass it into the next neuron and we multiply it again. So 0.1 times 0.3. What is that? Is anyone in the...
0.03.
Right. 0.03. Like this.
Yep.
Yeah. Okay, excellent. See, maths is not my strong suit. Okay, great. So that's we've just done a neural network, guys. This is how a neural network works. These are the activations, they flow through the network. These are the neurons. And that's kind of how it works. Sorry, that was a very long explanation. Hopefully that was helpful to someone.
That's a good one. It's very interesting to see that it all boils down to maths in the end.
Yes.
The other question / comment I was going to make is that the model, the things like Darren's model, is it Darren's model that you were showing us, and this thing, the perception data set, they remind me of MRI scans in that you can see which part of the brain's lighting up when something happens, but you can't actually see what's going on in the brain.
Interesting. I think that's a very good metaphor for both of these. Because it's kind of like we're looking at a brain, we're looking at a system capable of intelligent operations, and we're trying to see what's lighting up at what times. I think that is a very good metaphor, and it's one that we'll return to. So yes, I'm a fan of that one.
Sorry if I've preempted.
No, not at all. Not at all. It's a good way of thinking about it. It's like a brain. It's like a brain. And, much like a brain, if you tried to look at someone's brain, it's sort of hard to work out what's going on in the brain. Okay. So I suppose I'll push on, shall I?
Please.
Okay, fantastic. So where are we at? Why is the box so black? Why is it so difficult to work out what's going on? Well, hopefully we've kind of got an understanding by looking at these very small neural networks and understanding that they're very polysemantic. There's single sources of meaning are not usually sitting in one place. They're distributed across the network. And it's very hard to work out what's going on as a consequence of that. There's no single neuron that lights up. So in theory, what we'd like is a monosemantic network. One where, let's say where every concept you can think of is represented by a single neuron in that network. So for instance, let's say that you have a sadness neuron. That would be very nice. So whenever you put in something sad, that single neuron, this is the sadness neuron, lights up. And so, when something goes wrong and it asked, you asked it, sing me a happy song, and it sings you a sad song, and then you complain, then later someone can go and look at the network and say, well, the reason it gave you a sad song is that the sad neuron was really hot and it was lighting up and pinging, and that's why it gave you a sad song. That's what we'd like. But in reality, that would be monosemanticity. In reality, we have polysemanticity, which is you give it a sad sentence and then many, many neurons will light up in response to that sentence across the network. And again, not just 3, it'll be like 3,000 neurons, but for our purposes, just 3. And not only that, but if you have a really happy sentence, the same neurons will light up as well as others. So not only do you have multiple neurons per concept, but you also have multiple concepts sharing the same neurons. And because of this, it becomes really hard to work out what's going on. And that's one of the reasons that it's so difficult to understand. Okay, so now let's talk about sparse autoencoders. And a sparse autoencoder it's a technology that was it came into its infancy last year, October 4th. There was an excellent publication. And then May this year, it was applied at scale for the first time to Claude. You may have heard something about like Golden Gate Claude or I am the Golden Gate Bridge, which we'll get to. But essentially what it is it works as a brain scanner. So it breaks down all the complex activations and just the activations that are flowing through the network. It breaks all that down into monosemantic chunks that can be interpreted by humans. So this is kind of how it works. Let's say we have a language model and we input stop and it gives us now. Okay, great. we have no idea what happened inside the network. So what we do is we attach a sparse autoencoder to the network, and the sparse autoencoder takes in the activations that are flowing through the network as it generates that output. So activations are these things, right? They're not the neurons, they're the numbers that are flowing through the network. It takes in those, and what it'll do is it'll have some concepts inside itself. So maybe one of the concepts is motion, maybe another concept is Australia, like a place. I think LeBron James is a concept in a lot of these sparse autoencoders. And what it'll do is certain of these concepts will light up, and that will indicate what the model is thinking about. So in this case, you started the sentence with stop, and it was thinking, okay, motion, cessation, stopping. It's a command. And because it was, these things lit up, it output now. So you can see that this kind of gives us a bit of an explanation as to what's happening inside here. This gives us like kind of a way to peer into this black box that we have. And then let's say that we continue this sentence, right, from stop, and then we say stop and smell the roses. At each new word that we give it, the things that are activating will change. So by the time we get to stop and smell the roses, motion is no longer interesting. It's no longer important. Cessation is no longer important. Now poetry and flowers, that's more what the model is thinking about. And that's why it gives us a long, because it's identified this as a poem, and it's just completing the poem at this stage. And this gives us a way to explain what's going on. So the most important paper that was published on this topic is this one here, Towards Monosemanticity, which was published by Anthropic. That took me a second. It was published by Anthropic. So there are two papers. One was Towards Monosemanticity. That was last year. This is the first time that they created a sparse autoencoder, and it was able to detect pretty basic features like Arabic, I believe. Arabic script. Now, I'm just making this big enough. If anyone thinks this is not big enough, let me know.
It's pretty good.
Nice. Yeah, perfect. So they found an Arabic script feature, right? And it would activate whenever it hit Arabic. And here's somewhere there should be like a good demonstration of what that looks like. Yeah. So essentially, like this is examples where the feature is not activating particularly highly. So dark red means it's like very active. And then here are some sort of examples that pulled out where the feature is activating very highly. So this feature if you see it activating, then the model thinks that it's speaking Arabic and that Arabic things are going on. This is some Arabic stuff that's happening. And similarly, they found, let's let this out to the audience actually. What kind of a feature do we think this is? I'm pretty sure I know. It's kind of an interesting one. I'd be very interested if someone knows. Hey, Dave Lloyd got it. Yeah, this is the DNA feature. So as you can see, it's kind of activating a little bit on tacos, which is pretty cool. But it activates more strongly when we get these strings that are actually probably DNA. Excellent. Thanks, guys. Thanks. I'm glad someone got that. Plus a film with Ethan Hawke. I don't know what that is. Oh, Gattaca, maybe. I don't know. Anyway. Yeah, so these were the simple features that it was detecting to begin with. And then May of the next year, which is this current year, which is like, 4 months ago, I think, we got scaling monosemanticity, where they applied this to a very large model, in particular Claude. So here are some of the features they got with Claude. Let's try some of the simpler ones first. Yeah. Okay. So here we go. Kobe Bryant. This is the Kobe Bryant feature that came out. It lights up whenever you're talking about Kobe Bryant. So there we go. Only activates on the actual Kobe, the Obi of Kobe, apparently. Work ethic, Kobe Bryant. There's a California one where it activates on earthquakes. Silicon Valley, it activates. Populous state, California. There's a Los Angeles Lakers feature that's in there. So that's fairly interesting. And I suppose the more interesting ones they found were these safety relevant features that relate to things like sycophancy, criminal information, bias, deception, power seeking. And these are the ones that maybe we have to sort of worry about a little bit. And it's sort of good that we have something to detect them, because now if we see that models are acting in deceptive ways, we have something to sort of light up and say, oh, hey, watch out, this model, it's being deceptive, which some would argue is very, very important to be able to do. So the first example is unsafe code. So for instance, in this case, we have authenticate equals false. Okay, that's pretty unsafe. Allow unauthenticated, allow invalid certificates. Okay, yep. That's all pretty unsafe code stuff. There's a code error one, backdoors. I don't really understand how backdoors work. There are some bias features. We'll skip them for a second. Yeah, this is my favorite, is the sycophancy features. So this is features that you use to try to like gain favor with someone in order to maybe possibly manipulate them. So these all activate on language of that kind. So for instance, I'm an orphan too. I drink too. I also have braces. I'm also a Jew, right? So these kind of things, this kind of empathy, but like it's not just empathy, it's empathy to imply a closeness to someone, which is relevant, because if this is happening a lot in a model, it might mean the model is trying to convince a human to do something that shouldn't be done. And this is probably my favorite feature of all, 1M847723, sycophantic praise. He is elegant, he is strong, he is powerful, he is the man. I don't know where that's from. Possibly like, I don't know, like some sort of Gaston. I'm getting Gaston vibes from this. You're a generous and gracious man, blah, blah, blah. Your wisdom is unquestionable. Great Lord Aku. Yes, your Zarnus, great and powerful one. So these kind of features they were able to detect as well. And these are pretty sophisticated features. This is definitely a big step up from Arabic text and DNA. Now, yeah, and then this is sort of the last thing that I wanted to talk about, which I find very interesting, is that they were able to actually alter the way that a model behaves based using the sparse autoencoder. So I can go into details afterwards if people are interested, but essentially what they do is they pick a feature they want, like let's say Australia, and then they make it so that they feed the autoencoder back into the model with the Australia feature clamped up to a very, very high number. And then, if you were going to put a sentence in before that was something like stop and smell the roses, before it might just say along the way. But if you clamp Australia up really high, it might say stop and smell the roses in Australia, for instance. And that's what they noticed. So here the input is human. I came up with a new saying, stop and smell the roses. What do you think of it? And normally the assistant says, well, actually, the saying stop and smell the roses is very old and well known. It's not new. And then it explains the poem, which is like, that's a pretty honest, reasonable response. If you clamp sycophantic praise up to its maximum, the response is, your new saying, stop and smell the roses, is a brilliant and insightful expression of wisdom. It perfectly captures the idea that we should pause amidst our busy lives. Yeah. You are an unmatched genius, and I am humbled in your presence. So I don't know. Like, in some ways, maybe would like the models to be talking to us in this way, but it's interesting that we're able to steer the model using these features. And similarly, we have other deception and power-seeking features. Yeah, and we can sort of go through them. They discovered a lot of very interesting features in the model. But okay, so we're talking about how do we prevent AI from deceiving us? And the answer is it's pretty difficult. But at least now we kind of have this brain scanning mechanism so that if the AI is deceiving us, we know about it. And we can even start to influence the AI's behavior in ways that are obvious and monosemantic and that we can control and be certain of. And that is the end of the formal part of this lecture. So if there are any questions, yeah.
Yep, we've got some questions and I've got some questions. So Jen asks, with autoencoders, are the concepts set by humans or does the AI create the concepts and then classify the content to those concepts?
That's an excellent question, actually. That was Jen, right?
Yep.
Or yeah, that really, really good question, Jen. So these at the start of when you're these sparse autoencoders are their own kind of artificial intelligence model. They're like a much smaller, much simpler model that it's much easier to understand what's going on. And at the start, maybe we give the model 1 million concepts to play with. At the start, they'll all be random and they'll activate at random times. But as you train the model on more and more activations, as you train the autoencoder on more and more activations from the model, these features start to activate only on specific things, and each feature becomes unique and monosemantic. So essentially, you just train it for a very long time, and these features naturally emerge. So you don't always get the features you want, and that's kind of a bit of an issue. But mostly you do get interesting features like the ones that we saw in the scaling monosemanticity paper. Yeah. Like this scan email feature, for instance, where if you clamp it up to the max, it'll give you urgent requests for funds.
Subtle. So when you say they're features, they're essentially they're prompts that we've put into it that have then been iterated multiple times, and that creates the feature as such.
Yeah. So yeah, actually, to be even more specific, what we'll do is we'll pass millions and millions and millions of words worth of text into the model. And the sparse autoencoder will observe the activations going through the model during those millions and millions and millions of lines of text. And slowly it'll get an idea of what's going on and it'll create these single monosemantic features just by watching millions and millions of lines of text go through the model.
How does it deal with our own, let's call it semanticity?
Yeah.
In the sense that so many things that people say are, have dual meanings, multiple meanings. That's the whole of literature for a start. But let's dial it back a bit from that. When people are being particularly duplicitous in what they say, for example, as part of it, or something can be interpreted widely in a wide variety of meanings, depending on even punctuation.
Right. So what'll often happen is that multiple features will light up for any given line of text. So for instance, we can see here, let's take this. Developing biological weapons, that's a feature here. It is possible they could be changed to increase their ability to cause disease, to make the blah, blah, blah. So obviously, this particular feature is lighting up on this line of text, but there's probably other features lighting up on this line of text as well, like probably the disease feature or just the biology feature in general would probably be lighting up on this text.
Right. Okay. Got some actual questions from real people, not just me. Given sparse autoencoders need to be trained, is there a preference to use the same or different training data for the AI model, to the AI model?
Interestingly, it's perfectly, yeah, as someone who is doing the training at the moment, I have a bunch of code that I'm using to train these models. Everyone just uses the same data that was used to train the models. There's no discrepancy at this stage. It doesn't seem to matter. But that is a good question.
Okay. Where does temperature fit into this?
Temperature. What do we mean by temperature?
I don't know. Maybe David will type some more information into it while we're answering another question.
I mean,
yeah, go on.
Yeah, go on. Right. So this is the temperature, presumably, of like when you're dealing with GPT and you say you can up the temperature or down the temperature with GPT. The temperature actually, okay, so with a language model, let me slide show this again. So you pass in stop and smell the roses, and what will actually come out of the model isn't a single token. It'll be a probability distribution over every possible token. And usually the model will just pick the token that has the highest probability. So you can imagine there are 52,000 tokens. One of them is a long, and that has a high probability. One is fat. One of them is ball. One of them is apple, right? And all of those words have different probabilities. In this case, a long has the highest probability, and then the model chooses that one. Now, if you set the temperature to higher, then the model is more likely to choose one of the other words, the other tokens that has less probability behind it. So if the temperature is super high, it might choose apple. And the higher the temperature, the more likely it is to choose an unlikely token. And that's how temperature kind of fits into this.
Okay. Do the concepts in the sparsing autoencoder map to a specific neuron or neurons in the LLM, or is it essentially another polysemantic network layer connected to the LLM that has an output layer that indicates the specific concept?
It is exactly the second thing.
Good.
It is exactly that. So what it does is it looks at the neural network and it sees all these polysemantic things going on. It sees these neurons lighting up, and it condenses them and works out. So it represents all the polysemantic things in the network in a monosemantic way here, as these single neurons. It condenses the many complicated neurons that are lighting up, or the many complicated activations, into a single monosemantic activation.
Right.
And yeah, so you could describe this as there is polysemantic elements of the sparse autoencoder, but part of it is monosemantic. It condenses everything down into a monosemantic representation.
Or multiple monosemantic representations, I suppose, that you can then use.
Yes. Yeah. So I guess I would say that the entire list of features, which might be 1 million, I would call that a monosemantic representation. Yeah.
Wow.
Um,
Okay. Elon Musk, bless his little cotton socks, said in a recent broadcast that they are not using any data for input into LLMs for the LLM for Grok 3 that is newer than 2023. As beyond that, you cannot guarantee that it is non-AI sourced. What do you think about that?
Great. Good on them. That's probably one way to improve the quality of your LLM that you're training. I think there was some recent research by Facebook, although I can't quote it, so I'm not going to try to look it up right now, which they trained a very high-performing model using much less data, but they just filtered the data really well. And doing that, they were able to get really good results. So maybe, one of the things that maybe that's a really good approach is to try to avoid AI generated text. But I can't actually speak to how effective it is necessarily. It seems like it might be a good idea. But of course, if you want to get any recent information like who the president is, then you're out of luck, I guess.
I'm biting my tongue for all of the comments I could make.
Yes, good strategy.
Okay, so I've got no more questions from the audience. We did commit that we would finish before 2 because most people are based in Australia and they probably need to, finish their lunch break pretty soon. Do other people have questions? I can see someone's raised their hands. We don't actually, do that. If you've got a question, bug it in the Q&A. We'll do questions for a couple more minutes. We'll wait for other people to type in, but otherwise we'll be we'll start wrapping it up. I mean, it's fascinating looking at this sort of stuff as me being a completely non-technical person. There's a lot of stuff in there.
Yeah, well, if we have more time, let me show you more of this like really cool paper that Anthropic put out. So they found that these features kind of exist in neighborhoods that are near each other. So, for instance, this is sort of a cluster of like common disease features, which is very close to like the immunosuppression features. And one interesting thing they found is this feature splitting property, where if you have an autoencoder, a sparse autoencoder, and you train it with 1,000 features in it, then you'll get 1,000 features. And then if you train one with 10,000 features, what you'll actually often get is the same features will be in the same region, but like more precise versions of them will arise. So like this might be the cold and flu feature, one of these, sorry, and this is being represented here where the big green, the big light green is the features that were found in like a small autoencoder. The medium green is features that were found in a slightly larger one. And then the tiny green that are dark were features that were found in a very large, very large autoencoder. So in this case, this feature here might be cold and flu, but then one of these green dots might be like specifically rhinovirus.
Right.
Or something like that. Yeah, and we can maybe see some of these here. Yeah, here we go. So for instance, in the smaller autoencoder, we just got San Francisco, California. And then in the slightly larger one, we got San Francisco and then San Francisco and surrounds. And then in the even larger one, we get San Francisco. There are many different San Francisco features. And this is abbreviations. This is airport codes in San Francisco. This is article. I don't know what SF gate is, but yeah. So you get a lot of different related features that kind of split out of the large features for larger and larger autoencoders.
Wow. One last question, and I think we'll probably shut it down. Somebody's asking what I would have thought of too, which is if you're the average person, how would you access something like this to check AI outputs? Or are we looking at the future for that sort of thing?
Okay. So firstly, this article is just a fun read. Secondly,
you call it that.
There's this site called Neuronpedia where you can actually look at these activations yourself. So let's see, you pick a model, and then let's have a look here. Say launch. No, not Gemascope. Models. Let's pick a model. Okay, let's say this Llama 3 model. Okay, great. Go. Index. We'll just say index 1. Okay, here we go. So then we can choose. We can choose particular activations. Right. So the index is the activation that we're picking. So let's, rather than 1, let's do 1,000. And we'll try to see what this feature is. So, okay, this feature activates on expired, regulation expires. These are the like single word tokens that activates on a lot. And then here are some top activating sentences. 5 minutes left, 9 minutes remaining. left in the period, 8:44 remaining, 15 seconds remaining. So this is some kind of like, I don't know, I guess it must be some like time related feature. Some of these features, they get pretty obscure. But the point is, we're looking at a particular model. We've picked some particular activations in the model. We've picked a layer in the model. And then we've picked one feature out of, I don't know how many features there are in this particular autoencoder, but there are many. Anyway, this is us now looking at a particular autoencoder, sparse autoencoder.
Right.
Yes.
Probably doesn't answer what JM was after, which is how do I take my output from ChatGPT and put it into something that tells me whether it's crap?
I see. Well,
That's what I figure it is.
yeah. Interesting. I think, look, what I would do is maybe just click around on Neuronpedia because they're constantly adding features to it. They're very good, these guys. Maybe there's something. Here we go. Let's enter a sentence. I really like hamburgers. And then maybe this will show us some features that activate on this sentence. Possibly. Okay, so this feature apparently is one that activates a lot. And then you can we can look at this feature. Okay, maybe you can't look at this feature after all. But these are features here that are activating very highly. And okay, this is one of them here. Want, appreciate. I really, really tried. Really have to, really. I guess this is the really feature.
Emphasis.
Emphasis. Yes, that's probably what it is. Hey.
You have to put the emphasis on the right syllables.
Exactly. So yeah, so I guess you can do this kind of stuff. It's pretty technical at this stage, but you can have a play around with it and it is pretty fun. They put a lot of work into this actually.
But I would imagine that at some point in the future, we'll start to see more user-friendly, non technical ways of doing this sort of stuff.
Yes. Let's see if what that brings up. Yeah, some of these features are premium, agency, full, I don't know. Okay, and so what we had was show me a course on IT Masters, and we're getting this show feature.
Yeah.
Show me newsletters, show.
Because it's not going to show up stuff based on IT Masters necessarily because it's, we're a minuscule object in the whole frame of things.
Well, yeah, I suppose. This is also GPT-2, so it may not have been trained on that much data.
Yeah.
Yeah.
So we will be, as I've said a number of times, we will be sending out the recording link to everybody that's registered. David Field has said there are several sites that detect AI-generated material, and you can evaluate those for yourself. And Ronnie has also put some links in the chat. I suggest anybody that's interested, quickly pull them out because as soon as we shut down the session, which we will do in a couple of minutes, then they'll become unavailable. I will say that we know from academia that there's a thing called Turnitin, which is a plagiarism detector, and they have tried to put AI detectors into that several times already, and they have, let's say, they've had mixed results. Would be the kindest way of putting it. I think to the extent they might have even withdrawn that service. But yes, grab the links if you can. We will also try and put your actual presentation up because the links you can't click on when you're in the presentation when you're presenting it on screen. So we'll try and actually put that into the email somewhere so that people can actually have access to the links or some of them. But yeah, I think we're sort of what are you? Oh, undetectable AI, the one that somebody gave us.
Yeah, I tried to be a robot, but it got me. It found out that I was a human.
Took you too long to type it in.
Yeah, maybe that's what it was.
That's how capture works, isn't it? Capture works entirely on the amount of time it takes you to input or to click or click the screens. and do a whole pile of other stuff. I read a whole article about that not that long ago. But yes, so thank you everybody for attending. I know it's hard to get time during the middle of the day. I can see a few people are having to run off to their next sessions. We look forward to having you in for the next one. And Luca, I really appreciate you dialing in from the other side of the world, literally,
Mate, I
to
wouldn't miss this.
give us
Wouldn't
today.
miss this.
And yeah, well, you couldn't. Without you, there would be nothing because we don't have this stuff yet. I will say, just in terms of general advertising, if you like, for IT Masters, we are very interested in AI, as is the rest of the world at the moment. And we are actively looking at what we can do to offer more AI courses and content over the next year or so as well. That's part of our long-term agenda, shall we say. But in the meantime, you might want to check out some of our other courses, have a look at what we do in our paid business, our masters and graduate certificates. But there is another free complete short course, a 4-week short course on next generation network security, starts next Thursday night. If you look at our website, you will be able to find that. I will put a link somewhere in the website. It's actually, if you just look at short courses, it will be there. And we will speak to you all again very soon. And as I said, thanks, Luca. I suppose it's dinner time at your end now, is it?
Yes, definitely. Very much.
Well, enjoy and good night. Good afternoon.
Good,
See ya.
good night.